come back, I will now show you about something about molecular wear. Molecular design of molecular wear is simplest in molecular electronics. So, the basic thing is, in a broad sense, a molecular wear can be any molecule that is able to mediate electron transfer along the chain, okay, between donors and acceptors. So, if I write here in a cartoon form, but before I will tell you the several mechanisms are possible for molecular wear. That is, number one would be our familiar photo-induced electron transfer, photo-induced electron transfer. This one mechanism can be used in devising a molecular wear. Then number two could be electrochemistry of electroactive assembly, means you can put the metal ion charges metal ion can be +2 to +3 easily. So, that electron can be transferred and all that. Okay. And number 3 is conductance. So, these 3 are mechanisms based on which molecular weirs have been assembled. Okay. Molecular wear become very popular recently, and so many groups all around the world, they have made or reported so many molecular weirs. Conductance. So, here is a simple example of if I have to make a photo-induced electron transfer based molecular wear, I will put a donor here, donor in one corner, then a bridge. This is my bridge, and then acceptor. And remember, this length of the bridge can be really long, okay? Can be really long, this bridge. For example, let me draw a molecule that is really have been synthesized, okay, where you put a donor and then this is the bridge. Acceptor, okay. And here this and this N can be really big, and these molecules, I mean several nanometer of length, okay, they have been realized, very long can be realized. So, it is not a problem. I will now show you some of these photo-induced electron transfers that we decide that we shown in the very first day or second day. For example, okay, this particular porphyrin no porphyrin. Yes. One, two, three, 5. Okay. Similarly, okay. Okay, and then double bond, single bond, double bond, double bond, single bond, double bond, double bond, then single bond, double bond, double bond, double bond, double bond, yes, single bond, double bond. Okay. So, this is one side. I have to make the other side also. This I made electroactive, not photoinduced. AR. Zinc. Zinc is bound inside the porphyrin ring. AR. AR. Okay, zinc is bound in the porphyrin ring, and okay, double bond, double bond. Okay. And then let me draw this way. Okay. It's not this. This is my porphyrin. Okay. Iron is bound here, chloride. So, okay, then same. So, like this. Okay. So, now we did that, and electronic transfer rate will be, rate is also given 8.8. So, pretty fast rate, 10 to the power 9 per second. So, electrochemically we can transfer electrons from here to here. Okay. This is the direction electron can transfer. So, this is one example of a molecular wire. Okay. Another molecular wire example, this is also a molecular wire. Another example, I will not tell you many examples. Another example is, it can have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 hexadentate. It binds like this, then you go, keep on going. My God. So, some of these are very, very long. I do not have the figures with me. There are difficulty in synthesis, that is the problem. Okay. Okay. Oh, n, and this is m will be n minus 1 plus, and this is n plus, n minus 1 plus this, 1, 2, 3, 4, 5 and 6. Okay. So, this is another, and this chain can go long and long. I have seen one molecular where you have this porphyrins, 10 of them long goes on. So, this way the electron molecular wire, through this molecular wire electron can transfer, electron will go under, will be transferred from here to here. Okay. I made a mistake, will transfer from here to here, this side, because this is a higher oxidation state, lower oxidation state. So, it can go from here to here like that, if I put some more electron here on this side. Okay. Then I have another, for example, that is ruthenium. Oh my God, ruthenium. For example, forget it. I will tell you that you have ruthenium 2 and ruthenium 3. Okay. And you have several go like this. So, go like this n. Okay, like this, and then others are taking care of other. So, you make ruthenium where 5 coordination sites are very well done, fixed. And why you take this ruthenium and all that? Because they are heavy metals. So, if you take heavy metals make strong bonds with ligands. Okay, because the 5D, 6D, this kind of metals, what will happen? Is a 6D metal, then what will happen? 6D and this nitrogen can overlap very well, making the metal to nitrogen bond very strong, so that it will be very stable. Stability is also important, because when you go from ruthenium 2 to ruthenium 3, sometimes it may break away and then you go. So, these are the different types of molecular wires. Okay. I will not tell you many examples, same thing. Now, I will tell you a very important molecule. Okay. It was reported by Jean-Marie Lane. This is called a molecular switch. Let me draw this molecular switch. This drawing have to be perfect. So, I will draw no more what you call S. Okay, no more cartoon. Okay. This is down, this is up. N plus this. Here, here, here. This is one side, the other side is same. Other side will be same. S. Okay. Then okay. Positive. So, this is the compound, and what about here? What about here? Perfluoro. All the hydrogens are replaced by fluorine. So, I say perfluoro. Okay. When this is closed at this point, closed, then electron will conduct through this. Electron can conduct from here to here. When this is closed, and when it is open, this will happen. Okay. 1, 2, 3. 1, 2, 3. Okay. And then sulfur, sulfur. Then this. Okay. This exactly is necessary, that is why I am taking so much trouble drawing this. Otherwise, I could have easily get away with okay. Okay. So, this is open, circuit is open. So, my circuit is open. Okay. So, what happened? Electron not conducting, electron will not conduct because circuit is open. So, like my switch here, an electric switch, if I push it one way, circuit it is off, light is off because circuit is open. If I push it the other way, then the again light will come because circuit is closed. So, in this particular molecular switch, okay, electron conducting in this case, electron conducting electron not conducting here, open. Electron not conducting because it is open. Okay? And how to get these two easily? This is important. I can go from open to close if I heat it with, I can go from open to close if I heat it with 365 nanometer light. If I heat it with 365 nanometer light, I can go from open to close. So, like my switch, like my finger, I put the switch off, okay, or on. So, I put the switch on maybe with my finger. So, here my finger is here the instead of finger, this is 365 nanometer light. So, electron will start conducting from here to here. And if I allow it to, if I heat it with 600 nanometer light, 600 nanometer light, my circuit is open, electron is not conducting. Okay. So, these are the, this is a very important design, supramolecular design, where is acting like a really a switch. Okay. You heat it with 365, electron will conduct from here to here. You heat it with 600 nanometer, it will stop. So, switch light on and off means electron is moving and not moving. So, I have completed here logic gate, I have completed here logic gate and molecular wire and molecular switch. Let me not write. Now, there is another property that we will be discussing from next class by I want to introduce today itself. Let me introduce today itself. There are certain molecules, okay. There are certain molecules, if you heat it with electromagnetic radiation means light is a electromagnetic radiation, and there are some molecules, okay. There are some molecules where the polarizability is directly proportional to the E. My directly proportional is does not look very good. So, P is proportional to E means polarizability. Very simple example with polarizability I tell you. You have a tennis ball or a rubber ball, like we play rubber ball, you can squeeze it, right? You can squeeze it, and you have an iron ball, solid iron ball, you cannot squeeze it. So, polarizability of this iron ball is low, or it is non-polarizable as a matter of fact, but this polarizability is quite high of the rubber ball. So, polarizability actually in this case, in molecular case, polarizability actually is the deformation of electron cloud, okay, electron cloud deformation. When I squeeze a rubber ball, you know what happens, rubber ball will become deformed. So, similarly, some molecules are there which are polarizable. So, or in other words, polarizability high. So, those molecules, it is with those molecules. So, it is proportional to E with ordinary light. That means, with ordinary electromagnetic radiation, polarizability varies linearly. So, P is equals alpha E. Alpha is the polarizability, and alpha is the coefficient of polarizability, coefficient, or P is the polarizability of the molecule, E is the electric field. Electric field is coming from where? From light, because light has electric field and magnetic field associated with it. So, therefore, that is the case. Now, if a molecule has high polarizability, that means it can be deformed and all that. Which molecules? Which are aromatic kind of. So, those molecules, if we heat it with electromagnetic heat it with laser light, you know, laser light is very intense. So, we heat it with laser light. Laser light is very strong intensity. So, if you heat it with a strong intensity laser light with those molecules, some molecules, I will come to that, okay, then P is no longer proportional to E, but P varies at P equals alpha E plus beta E square plus gamma E cube plus it goes on like a series. Okay. So, this is if P is proportional to, when P is proportional to alpha E, then we call it linear, but when P is not proportional to E, we call it non-linear. So, some molecules therefore, some molecules are there whose polarizability varies with varies non-linearly in presence of a laser light. Okay. So, this I will take up from next day onwards. Thank you.